Hi everyone, and welcome to our spring break video, the first one, part one, dealing with your assignment that I gave you before break. If you have lost it or forgotten it, remember it is on Classroom, so that you can get a hold of it there. But let's get started looking at problem number one. First up, when we look at problem number one, this one is dealing with a lot of rates. We have rates of water going into a pipe, rates of water going out. Okay. First thing you got to keep in mind, you have to remember, is that when I integrate, the integral of a rate function is equal to an amount. Now the other thing, so you have that to keep in mind. The other thing you have to look for on this one, and we do have it there, is an initial amount. And in this case, they tell us that initial amount at t equals 0, that the amount of water in the pipe is 30 cubic feet. Another thing you want to keep in mind, this is a calculator problem, okay? So don't try to be too much of a hero and integrate functions. When you set up a definite integral, go through and use your calculator to evaluate that definite integral, okay? You know how to do that. Don't try to go through and integrate something, because often what you're going to find in here, well, some of the functions will be things you can integrate. Like in this case, they give you a rate coming out of water coming out, and that rate of water coming out is a polynomial. Well, I know you know how to integrate a polynomial. Yeah, these are not hard. This would not be a hard one to integrate. It looks a little bit weird with the decimals, but it would not be hard to integrate. But at the other end, we have a rate of water going in. And in that situation right there, it looks rather easy because it's just 20 times the sine of an angle. Problem is that angle has a t squared. And going through and integrate something like that, in order to integrate that one by hand, we would have to have a t sitting outside of the sine function. So just plan on using your calculator, plus save the time, okay? Get that stuff taken care of. Now, in this case right here, part A, it's pretty self-explanatory. You want to know how many cubic feet of water is flowing into a pipe. You have a rate of water going into a pipe, okay? The next one they want to know is, and the next actually two really have to look at the rate of change of the water in the pipe. Okay, we want to know if the water is increasing or decreasing at time t equals 3. And then the other one is looking at when it's at a minimum. Remember, we're looking at the rate of water in the pipe. So you want to identify the rate of change of the water in the pipe. Well, we have a rate coming in and a rate going out. So the rate of change of the water in the pipe is really looking at the relationship between those two rates themselves. The rates of the water going in the in rate and the out rate. And we're looking at comparing these two. We're going to compare them, okay? Now the next one, that's for B. Now that also comes into play for C, but you have another thing too. We want to identify where it has its minimum. When is the water on the interval from 0 to 8? And notice that is a closed interval, 0 to 8. When is that water at a minimum? At t equals 0, t equals 8, or somewhere in the middle. Remember, since it's in a closed interval, it could be at the endpoints. So you have to identify the endpoint, what's the amount of water at the endpoints, plus you need to identify at the amount of water at the critical values. And the critical values are going to be when the rate of change of the water in the pipe is equal to 0. So again, for part C, that's going to deal with that comparison as well. And then the last one, really, it's just an extension of that, going through and saying, okay, you got the in rate and the out rate. We want to know how long it's going to take for that to get to be over 50. So they just want you to write an expression for that. You don't actually have to solve it. And part of the reason you don't have to solve this is because you can't integrate that whole thing completely. So you just want to write an expression involving one or more integrals. Well, you got... that's how you want to write it out is up to you. You have two rates, so you could use two integrals, or you could look at it in terms of one rate, in terms of the rate of change of the water in the pipe. Don't forget for C and D, don't forget the fact that you do have 30 cubic feet of water in the pipe at time t equals 0. Problem number 2 is another calculator problem, which is nice because of the fact that you do have, you're looking at these two regions, R and S, and the first thing they ask you is you're going to have to find the sum of the areas of R and S. Well, in order to find the areas of R and S, you do need to go and identify this intersection point. You got to find what that intersection point is, and the only way to do that is to graph it out. Graph it on your calculator and use the intersection command to go through and find that. Find that particular that particular point. So, and then remember on this one, in this one you got it's real basic in terms of finding the sum of the areas regions R and S. You have your top function and your bottom function. Top function that you're looking at. So there's a top function, bottom function for R, top function, bottom function for S, and use the limits of integration, basically looking at x's, to go through and do that. Now, for part B, the base of the solid whose cross section is perpendicular to the x-axis are squares. So remember, on something like that, for part B, you know, you're going to find a volume. You have to integrate an area. A volume is equal to the integral of an area. So in this case, they tell you the area of the faces are squares. So in this case, I know the area V is going to be the integral of side squared dx. So we have to identify what the length of the side is. So remember on that, just go through, draw in one of the sides, just a vertical line, and come up with an expression for the length of that side. And let h be the vertical distance for part C. Let h be the vertical distance between the graphs of F and G in region S. Find the rate at which h changes with respect to x at x equals 1.8. So on that one, for part C, you're going to have to go through and identify a function for h. H is the vertical distance between it. Well, keep in mind, the vertical distance, we found the vertical distance. In part B, we came up with an expression for the vertical distance between the top function and bottom function of S. That's the length of the side. So really, what you're going to want to do for H is find that vertical distance. Use the length of the side from S. Actually from B. And then just take the derivative of that and evaluate that derivative at 1.8. Okay, so that should go through and give you work with that one. And again, this is all calculator. So in terms of finding the areas, I'm using my calculator because especially I'm assuming, I don't know, I haven't found the intersection point right here. I'm assuming it's not a nice point. Like you have 0, 2, 2, 4. I'm assuming that that intersection point is something that's not super nice. Okay. What you're going to want to do on there, keep as many, like about 5 or 6 decimal points for that X coordinate, because that's what you're going to need there. Also, and then for part B, once you know what that expression is, you're going to work with that. It's going to be something that you're going to need to integrate. You're going to need to calculate or do an integral. There is nothing on this section, nothing in problem 2 here that tells me that would be a problem that you could do without a calculator. You're going to need to use your calculator for finding R, finding S, finding the answer for this one, the volume of the solid, and for finding the derivative. And in each case, for letter C, I would again not be a hero and take the derivative of, have your expression take the derivative. I'm going to use the nderiv command on your calculator, the numerical derivative command on your calculator, to do that one as well. So that's kind of how I look at that problem. It is a very, very, very much that the calculator is necessary. Problem number 3 is your first a non-calculator problem. So from here on out, the problems really don't allow a calculator at all. And these are some real common type of problem here, where they're looking at giving a rate, and if you look later on, they're going to introduce another person in there, and those, you see that type of comparison a lot. In this case, Joanna jogs along a straight path for t going from 0 to 40. Joanna's velocity is given by the differentiable function v. Select values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given at the table above. So you have this table up here. You're going to want to be aware of that and to focus on it. Make sure you really understand what's happening with it. So you have, here's the minutes up here. There's your velocity. Okay. Now, use a table to estimate the value of v prime of 16. Even though it doesn't say that, in this problem right here, you do know minutes, so I would include, or you do know the units, sorry. So I would include units on every single answer. So v prime of 16 is, the nice thing is they've gone through, there used to be a time when they would go through and say, use a table to find like v prime of 24. Okay, and so they'd have a couple different answers. In this case right here, what they're looking at, 16 is between 12 and 20. So what you're going to want to do is just find the slope. Your estimate for v prime is really a slope of a line. So find the slope of the line between t equals 12 and t equals 20 to give you your estimate there. And again, keep the units in there. Using correct units, explain the meaning of the definite integral 0 to 40 of the absolute value of v of t in the context of the problem. And then approximate the value of that definite integral using a right Riemann sum with the 4 subintervals indicated in the table. All right, so for part B, be aware of for part B, you got the absolute value of v of t. And that's an issue because you have at 24, her velocity is negative 220 meters per second, or meters per minute. You have to understand, think about what that means there, what's happening there compared to what's happening the rest of the way. So you want to keep that aspect in mind and what that meaning is. Now there's another thing you have to keep in mind too. When you're working with these things, there is a difference between distance and displacement. Okay, and that's really this relationship between distance and displacement is really going to be key for your understanding of part B, of what's happening in part B. Bob is riding his bicycle along the same path for t going from 0 to 10. Bob's velocity is modeled by this particular function here, where t is measured in minutes and b of t is measured in meters per minute. Find Bob's acceleration at time t equals 5. Well, that's not a hard one. This is your velocity. Remember that acceleration, so for part C, acceleration is equal to v prime of t. Okay, so that can help you out with that one. And based on the model B from part C, find Bob's average velocity during the interval from 0 to 10. All right, remember for part D on this one, remember the average value of a function of f of x is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, so on this one right here, again, there's a average velocity. Average velocity, if you knew positions, then you could find average velocities between 0 and 10. You could just find the slope of the line between it. But in this case, you don't know positions. So you're going to have to use this relationship right here to find the average velocity. Okay? Remember, think of it this way. This part right here, that integral tells me how far they've traveled, how far Bob has traveled from whatever A is to whatever B is. Okay? So that should be enough to get you going and get through some of the problems and some of the issues in problem 3. Let's take a look at problem 4. All right, now let's take a look at problem number 4 with the differential equation that you're given, which is dy dx equals 2x minus y. Now, this one should cause you a little bit of an issue when you look at it because you see 2x minus y. In terms of separating, that's going to be something that you are not going to be able to do. So there's a kind of a hint in terms of what's going to be happening later on. So what we have here, the first part is on the axis provided, sketch a slope field for that differential equation. Remember on that one that the slope fields, you're going to take each point that they give you. Now in this case, they have 6 points. First one there, 2, 3, 4, 5, 6. Notice nothing on the x-axis there. So you're just going to give me the slopes there. And really what's going to happen on that is they're going to want you to go through and be that as long as you are close to the slope. And by close, I mean if it's supposed to be a positive slope, that you have a positive slope. That if it's supposed to be a negative slope, that you have a negative slope. And you want to be relatively close to what the value is. You don't want to make something that has a slope of 1/2 be steeper than than something that has a slope of 2. Okay, but you want to go through and be pretty comfortable that you have positive slopes when it's positive, negative slopes when it's negative, and slopes of 0 when it's 0. Now for part B on that one, you have to find the second derivative. So you know for part B that dy dx is equal to 2x minus y. Well, in order to go through and find the second derivative, you have to take the derivative of that. And when you take the derivative of that, that means you're going to have to take the derivative of that with respect to x. So that's going to result in a y prime, which is also dy dx. So keep that in mind for part B. Now let's take a look at part C. Now in this one right here, we're going to let y equals f of x be a particular solution. So in this case, you don't actually have to find a particular solution. We're just going to assume that y equals f of x is a particular solution, and that it goes to, and it has the point f of 2 equals 3. So it goes to the point 2, 3. Does f have a relative min, relative max, or neither at x equals 2? The key part there is to think about what would be happening if, for the derivative at the point 2, 3, if you had a relative min, relative max, or neither. So think about that. Use that and to make your decision in terms of part C. Part D is a little bit trickier. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. In other words, for part D, what you know is y equals mx plus b. You know the differential equation dy dx equals 2x minus y. And oh, by the way, I also know from this first part that when I take the derivative of y with respect, when I take the derivative of that line, dy dx is equal to m. Okay? Use that information to go through and identify. You're going to want to plug things into this differential equation and use that to solve for m and b. Okay? You're going to want to use this information that you have here with this to plug things into here and use that to identify m and b. Okay, so that's kind of where you're at with that one. Good luck with it. We'll see how you do on it when we get back. Here's problem number 5. In this one right here, you're told you have a graph of f prime. So like I said, I always go and just kind of circle that or do something to highlight that so I can keep in mind what I'm looking at. So that's the graph of the derivative of f. Okay? And it's telling you that we have horizontal tangents at -1, 1, and 3. Well, that's just to tell you what the x coordinates are at the low points and that high point that you have there. Just remove any doubt on there. And they're telling us that we have these two regions here and here, which are bounded by the graph of f prime and the x-axis. And they're telling us in that case that the areas of each one of those, that this region, that's 9, and the area here is 12. So I have that. And I usually just kind of put a mark there just to go through and work with that. Now, so everything you're going to be dealing with here is going to be a relation, is going to have to deal with understanding what this graph is saying and how to use this graph to do calculus. So for part A on that one, they want you to find the x coordinates for which f has a relative max and give reason for your answer. Okay, now again, you have the graph of the derivative. So for part A, you've got to use that graph to go through and make a determination where this thing is going to have a relative maximum. So you got to think about what is going to be true about the derivative of a function when it has a relative max. And then for part B, on what open intervals contained in -1 less than x less than 4, so the values of x between -3 and 4, is the graph of f both concave down and decreasing? And again, give reason for your answer. So what you're going to have to deal with on this one is you've got to think about what it means to be both, in terms of the first derivative of a function, what that first derivative is going to look like when the graph is concave down and decreasing. Well, remember, concave down happens when the second derivative is negative. So think about what it would have to be true about the graph of f prime for the second derivative to be negative. And when it's decreasing, again, understanding what would have to be true about f prime for a function to be decreasing. So you have that. Part C, Find the x coordinates of all points of inflection on the graph of f. Give reason for your answer. Okay. Same thing. Going through and identifying, think about the points of inflection happen for part C. Points of inflection happen when the second derivative goes from positive to negative or negative to positive. So you've got to go and look at that and think about what that second derivative would look like. Now, again, for part B and C, if it helps to try to go and draw out the second derivative and you're comfortable with that, then go ahead and draw it out. Draw something out either right there on the graph, on this graph somewhere, or just make a graph off to the side. And another part showing what f double prime would, your approximation for f double prime, if that helps. But you've got to go through and identify, again, the points of inflection. So you got to think about what it means for what's the behavior of the first derivative when the second derivative is going to be positive or when the second derivative is going to be negative, to kind of go through and make your determination there on the points of inflection. Now, given that f of 1 is equal to 3, write an expression for f of x that involves an integral, and they want you to find f of 4 and f of negative 2. Okay. So, on that one, remember, we can have a function y f of x can equal an integral from a to x of f of t dt. So you have that aspect of it, and then you're going to want to go through and write the function something like that. You do have to keep in mind they're telling you f of 1 equals 3 here for a reason, and it's not just because it's pretty. It's going to be a key part in your solution on this problem in terms of your integral. So be aware of that. Also, in terms of finding f of 4 and f of negative 2, you have to keep in mind, because there's 1, to go to negative 2, we're moving to the left. To go to 4, we're moving to the right. So it's really going through and having you show that you really understand how these areas come into play for finding the values of those functions there. So be careful of those and be aware of what's happening there to go through and calculate f of 4 when you calculate f of 4 and f of negative 2. Now we get to problem number 6. Now, in this case, they're giving you a curve here, y cubed minus xy equals 2, and they're telling you, oh, by the way, when they say it can be shown, it's saying, by the way, the derivative of y with respect to x is equal to this. So, the first thing in part A, they want you to write an equation for the line tangent to the curve at the point negative 1, 1. Okay, so remember, for part A, you have two pieces of information you need to find the equation of a line. You need a point and you need a slope. And then you can use the point slope form of the line to get me the equation of that line. And remember on this one, they didn't tell you to put in slope intercept form. I'm just taking that point slope equation and I'm plugging the information in and I'm done. I'm not going any further with that. For part B, find the coordinates of all points on the curve for which the tangent to the curve at the point is vertical. Well, for part B, you have to remember, what does it mean when you have a vertical tangent? And the big key on that one is really what is happening with the slope. So you're going to want to use that. And then for part C, they want you to find the second derivative. Excuse me. They want you to find that second derivative of that curve at the point on the curve where x is negative 1, y is 1. So remember, you have dy dx. you've got to take the derivative of that with respect to x. Now, again, you got to keep in mind that that derivative is, because your dy dx you're told dy dx is y over 3y squared minus x. dy dx involves y. When you take the derivative of y with respect to x, you're going to get a dy dx again. So you're going to have to use that fact to go through and get everything in terms of x and y, and then evaluate it at x equals when x is -1 and y is 1. So be careful with this. When you take the derivative of this thing, remember the derivative of y with respect to x is going to be a y prime or dy dx. So use that as you're progressing through as well. So with that, this really concludes my hints video that I have for the first set of questions on your spring break assignment. Hopefully this helped identify some problems and helped clear up some things that you're in terms of what you're working on. I will go through, make up a second video probably in the next couple days, and I will post that as well. But at this point, this does conclude this particular video, and I hope you are enjoying your break and enjoying doing some calculus along with that. So have fun, and we'll see you in a few days.